they said, my name is Dr. Jake Turner. I'm also a NASA Hubble Fellow at Cornell University and the Carl Sagan Institute. And today I'm going to be talking about the ExoGemS Survey, exploring the diversity of exoplanet atmospheres at high spectral resolution with Gemini GRACES. And I would like to start by acknowledging my entire collaboration, the ExoGemS collaboration, because most of this work was done by multiple people in a collaboration, so this was very much a team effort. So Megan helped introduce this a lot to you, so this is going to be a review. So essentially, as the planet orbits around the star, as you can see here, basically, if you look at the phase versus the wavelength, you can see that the stars, if there's something in its atmosphere, such as CO, the wavelength changes based off where in the orbit the planet is at, because the radial velocity is changing. And then you can see in this plot here, the toroidal lines are basically stationary. So you can use the large Doppler shift to the planet to basically disentangle the spectrum from the host star and also the Earth's atmosphere. So it's a very useful technique. And this technique has been used for almost over a decade now for a variety of different planets, different instruments, and it's quite an interesting thing. You can study a variety of different types of planets around a variety of different types of stars. So it's really an interesting technique. So I'll show you a few examples of here of some of the conical from HD 209-458, which is a canonical hot Jupiter. This is the detection of CO by Snell and al. 2010, which I would say is probably the start of this field. And so you can see here basically the radial velocity of the planet in the orbital phase, and you can see right away, you can see this absorption on the trail, essentially. And so they use this to constrain that there's CO there, as well as some atmospheric things that were going on in the atmosphere. And basically started this field. So it's quite an interesting result. And then a result that I worked on a few years ago, looking at Cal9b, with Carmenes, we detected H-alpha in ionized calcium in its atmosphere. And so you can see here right away, you can see the absorption quite well here. And I put this dashed data line you can see here is actually the radial velocity of the planet. And so if you actually put this in the velocity space of the planet, you can actually get a spectrum of the H-alpha line. And that's what we show here. And so we're able to do this with H-alpha and also the ionized calcium lines, and compare this to atmospheric models. And we're able to constrain the density, the pressure of the density of these lines where they're formed. And we found out that this planet was basically going through non-LTE effects. So there was very interesting stuff in its atmosphere. That's just an introduction. And Megan introduced it as well, which is, I thank you for doing that. So the ExoGemS Survey, ExoGemS with Gemini spectroscopy for short, is an approved large program with GRACES on Gemini North. We observe in the optical, so it's complementary to Megan's survey. We observe from 400 to 1050 nanometers at a pretty high spectral resolution of 67,000. So going more into our survey, so we're actually observing the planet's smaller transits. And so I show here a normal transit of an exoplanet for those who are not familiar. And essentially, as the planet's going in front of the star, and when the planet enters the transit, and actually the spectral lines will be blue shifted. When it gets to the middle of the transit, it's basically 0. And then when it goes the later half of the transit, it's red shifted. So you should be able to see the spectral lines of in the atmosphere of the planet shift, essentially. And so I showed some examples here of some atmospheric models created by Aaron McDonald. And so these are the atmospheric models that we actually use to cross-correlate our data. So here I show again wavelength versus flux. And so you can see several of these molecules and these atoms have very distinct fingerprints. So that's how we can separate them from each other and also know that we're actually detecting what we're hoping to detect. And some of these molecules and atoms have hundreds of thousands of lines. So it's quite a unique detection. So it's really exciting. And so we're basically searching for everything in our spectral region. So we can search for H-alpha, we can search for calcium, iron, etc. We can actually look through the whole periodic table, which is really, really interesting. As well, we have some molecules in our wavelength range, TRA, VA, a little bit of water, and some hydrogen as well. So we search for pretty much everything to kind of see what's going on in our atmosphere. So we're trying to find these species across a wide parameter space of planetary parameters to see if there's any trends that we can notice. As well as we're trying to look for 2D and 3D structured in our atmosphere as much as possible. So we can look for abundances and temperatures with altitude and latitude. Specifically, we can observe multiple lines. We can see where those form. And it's an example from I show on top from our 2020 paper, outline B, where we detect that we can actually figure out the temperature and the density and the pressure where all of the 4 lines form, and then get some kind of crude 2D effect. And we actually show that there are differences in pressure and density and temperature as well. So that's really exciting. And we're hoping to do that with more planets as well. As well as we can measure atmospheric rays. This can either be latitude or also even altitude range from the bottom of the atmosphere. But we're hoping to combine with low resolution. So Megan talked about this before. We showed us there's this result from Gregory et al. That when you combine low resolution, high resolution, either from Hubble and hopefully in the future, being JWST, that we can get a better constraint on some of the atmospheric effects. So we're hoping to do that as well. So this is showing our observed sample. And so we have planet mass and planetary temperature, as well as the radius. And so we observed basically planets all the way from 0.7 out of the mass of Neptune. So it's very much a Neptune type planet, about 4 times the mass of Jupiter. And we also observed planets with the relative temperatures starting at 670 Kelvin all the way to 3,200 Kelvin. And then, so all the planets we observed are shown, are circled there. And the other planets that we show that are possible targets we can observe in our survey. Because the way that GRACES is set up, it's only on the telescope pretty much once a semester in a specific time scale. So we really can't pick individual planets, kind of like what Megan was doing, but we kind of just get a variety of different planets and hope we can observe a lot of interesting ones. So that's why I don't have names like Megan had on hers. So we're getting quite a range of planets we've observed so far. So, not surprising, probably. To an exoplanet person, we're actually going to talk about WASP-76 first, which you just heard about. So WASP-76 is an ultra-hot Jupiter, about 2,200 Kelvin, has many atmospheric detections, also with I-bends, as we just learned in the previous talk. But multiple, almost every, I think, high-resolution spectrograph on Earth has detected something of this planet now. And most importantly, as Megan discussed, there's also asymmetric iron that was detected. So the iron is not the same abundance across the entire transit. Because during the transit, the part of the atmosphere we're looking at slightly changes, this was indication that there's some 2D or even 3D effects going on. And so the first original thought was there was iron rain, but there were many theoretical studies showing that the thick clouds that happen in different parts of the terminator, scale height differences, et cetera, but all pointing to basically a 2D, a 3D picture of the planet. So we're now getting into more of a regime of looking at these 2D effects. And so in our survey, we looked at this with GRACES, and we detected ionized calcium in its atmosphere for the first time. And within a week after we submitted the paper, another group independently detected ionized calcium as well. So that was quite nice to see. And so we used this planet to basically calibrate our reduction techniques, as well as make sure the telescope was working, et cetera, et cetera. So we wanted to see the same thing other people saw. And so we also detected sodium. You can see the 2 sodium lines on top. Many different groups have detected sodium as well. And then we compared these to several different atmospheric models. And we realized that our calcium signal was a lot stronger than we predicted if you just use a normal LTE model. And so we think there are some non-LTE effects that are going on. So the planet is actually hotter than we would expect, or there are some strong atmospheric winds that are moving ionized calcium across the planet. So we're observing some really interesting stuff. So we also detect iron, and we detect the asymmetric ion signal. And so as Megan was showing, this is the systemic velocity versus the rate velocity of the planet. And so again, showing the dashed lines here is where we expect the signal, and we see it pretty close to that. And so we're able to redetect what people saw previously, but we're going to use some 3D models to actually get some more information out of this planet. So stay tuned for that. As well as we detect everything else that people detected, such as lithium and potassium, and I showed the potassium detection here. So we're thinking that ExoGemS Survey is working as we expected. So that's very nice. And so the next one I want to talk about is WASP-31. So here's where falls in the parameter space, somewhere between about Saturn and Jupiter in terms of mass. So S31 is what we call a puffy hot Jupiter. So it is pretty hot, about 1600 Kelvin. I would say about the mass is about half that of Jupiter, and it's about 1.6 the radius of Jupiter. And with low resolution with the HST, there was some evidence of chromium hydride. And so I showed the detection here. Basically, this is again wavelength versus the transit depth of the planet, and you can see that it varies, and there were some atmospheric models that we compared this to, and we see that there is evidence of chromium hydride. And I show the plot. This is the retrieval plot they have here, and for some reason it's not showing up very well. But yeah, we found evidence of chromium hydride, so we thought this would be an interesting target to look at. And surprise, and thankfully, we actually detect chromium hydride as well in high resolution. So you can see our plot here. Again, with systemic velocity versus the rate of velocity of the planet. And we get about a 4-ish sigma, about 4.2 or 3, I believe, detection. So it's quite interesting. And so we're able to detect this at high resolution and low resolution, which we can use to get some more interesting constraints. We haven't done that yet, but we will do that in the future. But what this tells us, if you maybe you've ever heard of chromium hydride, is that basically chromium-bearing species are very important for the formation of clouds, and we believe clouds are pretty much ubiquitous on all exoplanets. So it should hopefully tell us something interesting about how clouds form on these planets. As well as chromium hydride specifically could be an indication that there was accretion going on of solids during formation. So this could be a direct constraint to how the planet formed. So the next planet I'll discuss in our survey is WASP 85A. It's basically a typical hot Jupiter, so we wanted to look at it. And so we get actually a detection of sodium for the first time on this planet, which is not surprising because we detect the sodium on multiple planets. And here I show our detections. So again, wavelength versus the rate of velocity of the planet, and we see both lines pretty strong. So if we sum those lines together, we can get a spectrum here, and you can see it's detected quite well. We're eventually going to model this and see if there's any non-LT effects going on. We haven't done that yet. But the interesting thing about this planet is that it's around a very active star. And so we were not really expecting a little detection because activity kind of makes it difficult, but we would find one. So this is very helpful that even we can detect things around active stars, which is really useful because there's a lot of active stars. Specifically, we're starting to look with M dwarfs and some of these smaller planets eventually. So the next planet we're going to talk about is Happy 32. So I'll go into that. So yeah, again, Happy 32 is kind of a normal hot Jupiter, but there's some interesting things going on. So there was some previous observations with H alpha that showed there might have been early ingress as well as escaping atmosphere. So we actually confirmed that. We confirmed that there was H alpha. So I show here the spectrum of H alpha. So this is the wavelength versus the flux. And if you can see on the flux axis, this is actually about a 2 to 2.5% transit depth, which is quite large. It's a lot larger than the optical transit depth. So the radius that we're seeing is actually beyond the Earth globe of the planet. So this atmosphere is escaping. And there's not very many planets that we can actually detect their atmosphere escaping. So this is going to be an interesting observation for that. So it's going to be very important for understanding how atmospheric escape happens. And so we also detect ionized calcium in its atmosphere, and that doesn't seem like it is escaping. So we're actually detecting many different elements in its atmosphere, one that's escaping, one that's not. So we can actually learn some of that really interesting structure. As well as we see some tentative evidence that there's actually an early ingress. So I show here a plot of my data, the wavelength versus flux of different parts of the observation. And we see that we might have this early ingress, which there's only a handful of planets with that. So this is really, really interesting for our survey. The last planet I want to talk about in the last minute of my talk is GJ3470b, which is the smallest planet in our survey. Okay, there we go. So GJ3470b is a super puff. It's about 670 Kelvin, about 4 times bigger than that of Earth, and 0.7 that of the mass of Neptune. And we actually do not detect water in its atmosphere, which is inconsistent with radio recent observations. And not quite surprising because we don't have many of the water bands in our observations, but we want to look for it anyway. And hopefully we'll get some kind of constraint of why we're not seeing this in some kind of 3D structure or 2D structure of the water abundance, at least an upper limit. And we thought we detected ionized calcium in this atmosphere I showed here. You can see one of the ionized calcium lines. However, with future investigation, that's probably likely caused by stellar activity. So this definitely puts a lot of limits on what our survey can do, but it's also very interesting. So, on the next steps of our observations, we have 1 more year of observations left, and we're going to concentrate on targets that are observed by JWST, either currently or planned in the future, as well as other previously detected planets. So we show here some of the possible targets we can observe in the next semester. Parameter space in which we're trying to open up the parameter space, go to higher, smaller planets, higher planets, et cetera, et cetera. As well as we're going to try to produce some more 3D models to compare to our data. And this is an example of one of the 3D models that shows the temperature as you go from the night side to the day side, as well as the terminator, which is what transit observations are usually sensitive to. And you can see there's quite a gradient there. And so we're trying to produce more of these models to see if we can see these interesting 2D to 3D effects. And we're hoping to understand better the stellar activity because we have several stars that are very active. And we're trying to see if we can detect something in them, as well as we have several planets where we have no detections at all, and they're very similar planets that we do have detections. So we're going to try to see why that is the case. And so stay tuned for that. So the ExoGemS survey, in summary, we're hoping to explore the diversity of planets across a wide parameter space to understand exoplanetary atmospheres. And preliminary results show that we're doing a pretty good job so far. So this is just some highlight of some of those results. And thank you for your time.
Okay, thank you for an excellent talk. Questions in the room for Jake? Yeah, please come up to the microphone.
Thank you for your talk. I have a question. How did you select the target?
Yeah, so we originally, when we first started the sample, we were going to look at specific targets, but because there's only 1 week where GRACES on the telescope, we essentially just look through every possible exoplanet transit. We make sure it has good signal to noise, and we make sure it has a wide variety of rate of velocity changes throughout the night and the transit, so we can separate from the star and the planet. And so thankfully there's lots of planets now that are really bright, so we at least have 1 planet each day of the run that we can observe. And so it's more of just like we're getting a variety of planets instead of individual targets that we want to look at.
I see. Then another question is, how about the range of the ages of your targets?
Most of these are pretty, I think they're pretty old. We don't have any young planets, partly because a lot of young planets are very difficult because their stars are varying a lot, and we don't expect that we'll see. We did include some of them in our original sample, but they weren't observed. So far, we haven't observed any young planets.
I see. Thank you.
Okay, and next question in the room.
Thank you for your talk. This may be a naive question, but I was wondering, have you considered or would you expect there to be a trend in these chemical abundances and also the atmospheric escape with respect to the distance of the planet from the host star?
Right. So yeah, you definitely would. So most of the planets we are looking at are quite close to their star because we have to observe them within 1 night of observations. And so usually our constraint is about a transit duration of 5 hours, which means these are all orbiting within 2 or 3 days. Maybe 4 days is our limit. So they're all really close to their star. And so yeah, there's some, if the planets are really close, they're more likely to have an escaping atmosphere. But this is still an open question in exoplanets, because even some of the, like Cal 9b, for example, is, I guess I might have not said this, but it's the hottest known planet we know, about 4,500 Kelvin, which for people who study stars is actually hotter than M dwarfs and K stars. So this planet is actually like a star almost in a sense. But as far as we can tell, we haven't detected its escaping atmosphere, even though most everybody predicts it should be there. That's why we actually look for the H alpha, but it seems like the H alpha was formed pretty deep in the atmosphere. And so this is still a very open question in exoplanets of how we can detect it and also see these trends, because we expect there to be, but so far we haven't had enough detections to say that.
Thank you.
Other questions in the room? I have one. So the plot you showed earlier for the chromium hydride detection.
Yes.
My impression of this is that you have to go in knowing what molecule or atom you're looking for. What prompts you to say maybe there's chromium hydride in this planet?
Well, so partly because it was previously detected, but
Okay.
right now what we're trying,
Prompted them.
yeah, well, I think they ran a retrieval with just a bunch of stuff. And so what we're doing in our observations is we're actually cross-correlating our data with every known element and every known molecule, which takes a long time because there's a lot. And then usually there's most of those are non-detections. And so in this case, we started with chromium hydride because we knew it was might have been there and it was previously seen. So for them, yeah, it's the same idea. You want to try to see what's in your data. And so with low resolution, yeah, you run a lot of different retrievals with pretty much everything that could be there. And this is predicted by theory that it should be there. So that's also one reason why people were looking for it.
Okay, very cool. Thank you. Okay, last chance for questions in the room for Jake. Going once, going twice. Okay, well, with that, let's give a big round of applause for both of our speakers in this session.
Thank you.